Doing?
You Dr. Joe, just peachy.
It's just peachy for me. Thanks, Michael. Everybody getting their homework?
No, it's not everybody's here.
Okay, everyone who's here, did they turn in their homework? Sorry, I thought that was implied that I was talking to the people who are actually here.
Not everything's implied out there. And implied that it's not implied.
Apparently.
I can only drink for a day. Michael
I don't think that's going to happen.
I don't think it's
All right.
What'd you say?
I said we can only drink for a day, but Michael doesn't.
Oh. You would not believe this. I saw a pen walking back to the other day. It was exactly like my pen. And then the next day, I looked in my bag and realized that was my pen.
What?
What are we talking about?
I was really sad because it was like a nice pen. It was like one of those expensive.
I'm just stuck on the first part. You saw it walking.
Yeah, so like I must have had my bag. Like I have like one of the small ones. Like in here is like where I have all my stuff, and it must have fallen out one day because it was open, and I saw it like on the ground. Like I have that exact same pen, and then
Oh, you were walking and you saw it.
yeah.
See,
I thought the pen.
I was
Yeah.
walking.
Imagine.
We thought you were making fun and just being sarcastic.
That would have been funny though.
All right.
I'm not ready yet.
Not too bad.
I am. No, stop. Quit it.
Can you make a lot of my pen? Or, no, I don't think so.
That's to my knowledge.
Maybe
That's because the window is open.
No, it's not. It's not snowing. That is not snowing. That is not even trickling. What is it?
It's precipitating.
Yes, that's a good word. Because that's not precipitating.
Small amounts of frozen water.
Very small. Minute.
Frozen dihydrogen monoxide or whatever it is.
Oh, that was funny. When they spread that like hydrogen, oxygen is in the water.
Yeah.
Everybody like started freaking out.
Yeah.
And then they're like, "You people are just so dumb."
All right, so let's talk about confidence intervals some more. What's wrong?
She didn't get it.
All right, so let's talk about confidence intervals some more. So again, the whole idea behind the confidence intervals is to construct a range of numbers that is likely to contain your mean. And so before you take any samples at all, you want to try to figure out a method that's likely to contain the mean, well, at least for what we're doing right now, our means. What is likely to contain the population parameter that you're interested in. So again, the idea of being close together is that, oh my goodness, it's shifting everywhere. That idea that the probability that your distance, that your sample mean is away from your population mean is small. The probability that that's small is actually a large probability. So there's lots of, I understand there's lots of math symbols in this idea, but the whole point is that we're going to construct an interval around the mean. I want to make sure that there's a good shot that when I pick a sample, that that sample is close to the mean, based on some value that we will mean by close to. Okay. So if I want an interval around the mean, if I've got a normal distribution to start with. Laughing at my graph. You've had me for enough classes, you know my graphs suck. I don't know why you have to laugh every time. All right, so the mean, of course, for a normal distribution is there in the middle. I don't know why that's not even that bad. I've drawn much worse. I've drawn much worse today.
It looks lumpy.
Your axes, like,
Yeah, the axes are good. The normal distribution is ugly. Sure, okay.
Lumpy.
Okay.
My Louise ears.
Come here, I'll show
Actually,
you.
Michael's are pretty good.
Yeah.
Alright, I'll ask again tomorrow.
It's not any better. It's not any better. It's fine, whatever. You get the point. All right. So a symmetric interval around the mean would have a positive and a negative value to it. I'm using z's here. I don't really mean z's according with the mu. I would mean a 0 there if I'm doing standard normal, but this is the idea. All right, I want to have these numbers. I want to figure out, these are the bounds that we will get by picking the alpha. Okay? The z values that we're going to use, we get to pick the alpha, how confident we want to be. What we mean is, we want to pick, the alpha again corresponds to the probability that you're in this tail, right? So there's an alpha over 2 over here, there's an alpha over 2 over in here. Right? And this is basically your bad region, if you will. I don't want to be in that region, so I want the probability that I land in that region to be small. Okay? So when you pick sample means, you compute sample means, you want it likely to land in this and unlikely to land here. Okay? So the likely to land in here is that 1 minus alpha. So you're going to pick the alpha to be small. So that 1 minus alpha is relatively large compared to the alpha. All this is just this is just converting your distribution, your sample means, to a standard normal, and then these z-scores correspond to that standard normal. That's all it is now.
But within the probability, you have alpha over 2.
Mm-hmm.
Earlier if I were to just said alpha. That
It should be, if we're doing the two-sided, it needs to be z sub alpha over 2.
the one-sided.
And then the one-sided would be z sub alpha, and then we wouldn't have absolute value bars either.
Okay, and if we get that, would it still be equal to 1 minus alpha?
Mm-hmm. Because the alpha still is the idea of the probability that you get something that's far away from the mean.
Yeah.
Okay. So even if it's one-sided, then all of your alpha will be on one side. All right. So to that end, of course, we have certain values, and I still haven't put the normal distribution on here. We have certain values that correspond to alphas where we can figure out these z sub alpha over 2s. But we can use Excel actually to help us find these as well. I meant to copy the normal distribution. So, for example, if we wanted, say we wanted an alpha value, well, I'm going to need a keyboard because I actually have to type letters. So, say you wanted an alpha value that's 0.05. Right? So that means we would need an upper tail that has 2.5% chance of happening. Because remember, if we do two-sided, we cut the 0.05 in half, right? Well, we can use Excel to help us find these values, or use the normal distribution table. There we go. So if we start typing normal distribution, we've got all of these particular ones. The ones that we're interested in are the top 4, because all the ones that have little exclamation points are from old editions of Excel. Or I'm going here today, so I don't have to reach up so high. All right, so the only difference between the top 2 and the next 2 is that the one that says norm.s is the standard normal. So you want to type in a mean the standard deviation, if you've already standardized it. That's the only difference between the two. All right, so I actually want to use that in this case. I want to use the inverse one, though. I want the norm.s.inv, because what? Nah, I meant to hit the tab key. I always do that. Oops. I want the INV one. This is going to, so what the INV part means is that I want the X value associated with giving me a certain cumulative probability. So for example, if I put in 0.5 in here for a cumulative probability, what should I get out? What value gives me half of the probability of the normal distribution? What X value gives me half of the probability? What's it in the mean? So if it's a standard normal, I should get out 0, right? So if I put in 0.5 here, I should.
No.
No. What?
No.
Now, the reason why I did that is because apparently the keypad didn't catch up with me. Here we go.
You're too quick.
Right? So I should get 0, right? So it's looking for the value here. It's looking for the X value that gives me half the probability. Well, that should be the mean. For standard normal, the mean 0.
Oh, okay.
Yeah, that's what I'm saying. Okay. All right, so if I wanted a 95% two-sided confidence interval, so I want to leave 2.5% at the top, the cumulative probability at that point would be 0.975, right? So if I put in 0.975 here, we get 1.96, which is one of those familiar ones that pops up in that normal distribution table, right? What's that? You being a smart guy again?
Why couldn't you just divide alpha by 2 and keep the same thing from there?
Yeah, you could do it that way. So you can just do alpha over 2. Absolutely.
So is that?
The reason I did this is because those values are given to you in the table, in the book, as positive values. But you're exactly right. If you did, so what Grace was asking is if I just change this to, if I change this to 0.025, which is on the left side, I should get negative the value. You can absolutely do it that way. The table in the book gives you, I still haven't made a copy of it and put it on here yet. I apologize. Gives you z sub alphas and z sub alphas over 2s for alpha being 0.4, 0.3, 0.2, 0.1, 0.05, 0.025, 0.02, 0.01, 0.005, and 0.001. It's a lot of words. But Excel will do it for any of them. So if you, for some reason, wanted an 84% confidence interval, you can find the z value associated with it. Yes?
So for the numbers, you just take the 1.9. What do those mean? Because
No, so those are the z-scores. These are the z values that you're getting. The numbers that I typed in are, if you're British, sure, why not? So the numbers that I typed in were the probabilities here. So we're typing in a probability for a tail, and it's spitting out a z value that corresponds, that gives me that probability. It's that, if I look at the picture again, it's giving me these numbers on the x-axis. Okay. All right. So again, the idea behind this is that we can find this symmetric interval around mu. Now, if we rearrange what's inside the probability, you get that your mu, I guess I'll change this back over to black. You get that your mu should be in between whatever your sample mean is plus this z sub alpha over 2 times the standard deviation, or minus the same quantity. We're getting that symmetric interval again because, well, basically we're defining it that way, right? We're splitting up the probability of bad things happening to be too far below or too far above, splitting it into two pieces. And we know that the normal distribution is symmetric, so we split it up with symmetric probabilities, and so that's why we're getting the symmetric interval around it. Okay? So when you're doing these problems, all these problems are all alike. The things that are going to change are, one, I have a small sample. If I have a small sample, the normal distribution, even if the underlying distribution is normal, the normal distribution may not give me a good approximation, so I have to use the t-distribution instead. Okay. And then later on, what'll change is, how do I calculate this? What do I use for the standard deviation? The reason why we're using sigma over the square root of n here is because we have one mean, right? And we know the distribution of the sample means is normally distributed as long as the underlying distribution is normal, right? And we know what the standard deviation is. Remember, the variance is sigma squared over n, so the standard deviation is sigma over the square root of n. So the things that are going to change are, what do we use here to make sure that we are far enough left or right to make sure that we have small probabilities of the tails? And how do we calculate the standard deviation? The concept of the confidence interval is not going to change at all. Okay. This concept of doing a symmetric interval around whatever parameter we're trying to estimate, it's the same concept in the next 4 sections. And then we're going to talk about, if we want to make sure that our estimate's really a good enough estimate for our purposes, we're going to talk about how to figure out what size of sample we need. So really, it's the next 5 sections is all the same idea, which is why I said you're going to be watching the video for a little while, because everything else introduced except for the new forms of the distribution intervals. So I'm going to have you watch like 30 seconds and then come to class. Okay? All right. So let's talk about how this works. So let's do a specific example. Let's look at 6.2-5. All right. So let me see what I can do here real quick. Stuff minimized if I can. That's what the numbers are. Oh, and of course it went away immediately. There we go. So I want to type these numbers in a second. Oh, it's sideways. Great. There we go. Thanks. So you're able to crop it too, right? Well, that was interesting. That's because it's set on document scan. Done. Cool. All right, can I pull this into OneNote now?
Yeah, nicely.
Insert a picture from the camera. Oops, cancel from the file. I don't know. Look at that. There it is. Oh, stop making fun of my technology uses here. I am old. I can admit it. How's that? Is that better?
Yeah, that's longer.
You want me to make it bigger, or is that okay?
No, it's good.
Good. All right. Now, in a minute here, I'm going to go back over to Excel and type in those numbers. So, mainly because I need to figure out what the mean, the standard deviation are. And then I'm also going to show you another command on Excel as well. So, I'll give you a second to write those down if you want to write them down, or if you don't care, you can not care. They're in your book, obviously. Can't quit now.
1/3 of the value.
Can I do this? Hmm? No, that's what I'm trying to do. Because I don't need very much of the Excel on here at all, actually. Oh, stop it. Don't laugh at me.
I can just I can see you as you get older, just being yelling at some sort of technology. Like the technology's gonna talk back to you.
I already do that. You should be in my office when I get irritated with my computer. Hmm? What'd you think I was going to say? Probably what I say at the computer. Didn't remember to bring the external keypad here with me.
Yeah, that was type it out.
Oh, I would have. But there we go. I think I got them all entered. Hopefully I did them right. All right. So again, we could do this with the table to figure out what the... Sorry, what's wrong with Megan? Okay. We can figure out this to get your z-values with the table. But let's talk a little bit about how we would do this with Excel. I'm going to use Excel anyway to help me get the values. So to get the confidence interval, we need... Oops, of course the Excel went off. I need to know the z sub alpha over 2. I need to know the z sub alpha over 2. I need to know the sigma, the n, and the x bar, right? Well, the n's easy. They tell us it's 30. If you didn't know how many things were in Excel, you could use the count command and just have it count how many things are here. If you didn't know what it was. Magic. If you want to know the mean, of course, that's the average command. What's that? Did you already do that?
Hey, that's what I got.
Good. All right, so this is the n value. This is your mean. Okay. What else do we need to know? Standard deviation. So when you do the standard deviation, there's 2 of them that it can do. This STDEV.P means that you know the entire population, and you're going to calculate the standard deviation for that one. So you'll never use that one because you're never going to know the entire population. Don't do P. Okay. You want the S. All right. So standard deviation of a sample. All right. So then, again, highlight it all. You get that. So I didn't write. This one is. Everybody get these written down so I can actually make Excel a little bit bigger. Are we okay with that? Okay. Good. So let me move this down here then. All right, so then we also need our z sub alpha over 2. What was the confidence interval? Oh, it was the percent confidence, they said. I think 90. So what's that mean for that alpha is equal to? 0.1, right? Okay. Which means alpha over 2 is? Okay. So if I do the norm dot s dot inverse again, 0.05, right? Yep. Okay. So if I do, you can either do 0.95 or 0.05, it doesn't matter. One will give you positive, one will give you negative, right? So you get 1.645, which is also another familiar one, right? And that'll be what you'd see in the table if you're using the table.
So, really just I think it's about when you plug in to get the positive.
What am I plugging into the? Yeah, I'm doing 1 minus the alpha, yeah. The 1 minus the alpha over 2. I'm getting the top tail. You can do either. If you put in 0.05, you'll get negative 1.64. I just didn't want to see the negative, so I didn't put that in there.
Where did we get that from?
So it told us to find the 90% confidence interval.
Oh, okay.
So the alpha is 0.1. So we're doing half of that. Okay. All right. So now we want the bounds for the interval. So if I do the lower bound, I need to do what? So yeah, we'll do the mean, right? Then minus your what? Z sub alpha over 2 times all right, so B21 is the mean, right? B23 is your Z sub alpha over 2. B22 is the standard deviation of the sample, and then B20 is just how many was in the sample. So it's the square root of n. And then your upper bound, oops, if I can type, oh, for gosh. All right. Yep. So that's exactly what I'm going to do here. Just go back up here and change that. I just copied the text that I put into the cell and I'm changing the minus to a plus. All right. Yay! So there's our upper and our lower bounds for our confidence interval. I believe the answers that they do in the book, they'll usually put it in interval notation and use brackets. But if you want to write an inequality statement, that's okay too. The fact of whether or not you use brackets or parentheses is pretty irrelevant because again, we have a continuous distribution. So the probability that you actually hit one of those values is 0. It doesn't matter if you include or exclude the endpoints. Just the way it has it set up, it has it equal to, so it uses the brackets, but it really doesn't matter. So again, the idea behind this is that we've now created a range of values that hopefully contains the mean. We're 90%, in this case we would say we're 90% confident that the mean is between those two values. And again, the way we're, one of the interpretations that we're going to use based on this is we're going to say, okay, somebody came along and said that the mean was really 75. The mean is 75, and you do this test, and you're like, hey, you do this confidence interval, I'm like, I don't think the mean's 75. Okay? That's where we're headed with this stuff. You would say 90% confident.
Yeah.
But we don't say that there's a 90% probability. Because again, before we start constructing intervals, 90% of the intervals that we construct in this fashion will contain a mean. But once we have an actual honest to goodness interval, it either contains it or it doesn't. There's no probability associated with it. It's either there or it's not. I guess technically there is. It's 1 if it's in there and 0 if it's not, right? There's not a 90% chance that it's in there. It's either there or it's not. It's not in that interval 90% of the time. Because the population mean doesn't change. All right, does this idea make sense for what we're doing? Yep, okay. So there is another command in here that you can use for confidence intervals. So there's a command called confidence, which will give you, it will actually compute the entire z times standard deviation over the square root of sample size based on the alpha. So in this problem, the alpha was 0.1. The standard deviation is sitting there in B22, and the sample size here is sitting here in 20. All right? Yeah, Grace?
How do you do it with me?
It's not calculating with the mean. It's just calculating the part that's on the plus or minus side. It's the margin of error, yes. That's exactly what that is. Yes. Okay. So notice now if I took the mean, which is in B21, and subtracted this confidence thing that we just calculated, we get the lower bound. So it does it all in one chunk. Yeah, Ashley?
Mine has like confidence as like the little like outdated one.
Mm-hmm.
So is it fine to use that one?
Let me see. This one down here is what you say you have, the outdated one? It's the same syntax, so it should work the same.
Okay. I wasn't sure.
Yeah, some of them are, the old ones won't work right, but this one should be fine. Ooh. Oh, I did use the wrong alpha, thank you. Oh, I made a mistake. That never happens.
Never, ever in your career.
No, yeah, never. That was the first one. Ruined the perfect game.
The miracle didn't even exist.
All right. So yeah, the outdated one works too.
Well, that's what we
Yeah. This one?
Yeah.
So what this one does is it takes the z sub alpha over 2, the standard deviation, and the square root of it, and puts it all into one number. So all I did was just put that one number and subtract it from the mean.
Oh.
So if I go back over to this formula, so this 11.898 is this entire thing here. So if you wanted to, here I could take the mean and subtract the confidence. That's interesting. Confidence. Interesting. I don't know why it went away. That's weird. Confidence dot normal is for the, because it'll also do for the t distribution as well, which we're going to talk about here in a second. But 0.1 and the standard deviation and the sample size, you should get the same number. So I can do it all at once. This okay? All right, so what if we have small sample sizes rather than large ones? So let's look at, this is number 7. Let's see if I can, let me try to get a picture again.
Sure, do it.
Photography skills are amazing.
My photography skills are amazing.
Uh-huh.
Uh-huh.
I was just telling the truth.
That I can just do that way?
It's amazing.
All I care about are the values here, so I'm just going to get these.
I can try for it.
What's it matter if I make a trapezoid or not?
Well, I just wanted to travel with that.
Is it, what did you say? I'm sorry, Megan.
We also need to make the confidence interval.
How much? It's 95%.
$6.27,
Say it again. 6.2-7, yeah. Pictures. Profile. 95%.
What's the 95s?
How's that? Better? Can we see them?
Beautiful.
John, do you speak Spanish?
No.
That was good.
I know. I can count to 10. Not what I can do. There were a series of commercials back when I was in college that was selling this, like Rosetta Stone software.
Yeah.
Okay, so this wasn't Rosetta Stone software because that software wasn't that sophisticated, back hammering in tablets, right? But
Before there was that.
okay, was that back when the Rosetta Stone? Yes. But but they were tapes to help you learn how to speak certain languages. So this was Spanish, right? So it was all stupid mnemonic remembering how to pronounce things, but nothing about the actual syntax at all. So they were saying, that's the way it is, I believe was the phrase they were doing, was SOCKS. So it's spelling socks. And so the person in the background will go, oh, Spanish is easy. Or if you stand on a chair, you'll see a loose light. So apparently chairs see a loose light, from what I understood from the actual.
Yeah. Wait, what?
It was just really bad.
It's really bad puns to help you try to remember Spanish words. The SOCKS. Ooh, Spanish is every time I finish the phrase, it was, ooh, Spanish is easy. Every single time. It was really, really bad. Yeah. Ooh, Spanish is easy. Yeah, nothing to do with syntax or anything. Great.
Every video we watched in Spanish in high school was so cheap.
Yeah.
It's always about like chupacabra.
I wish I had cheesy videos for my German class. I just had really weird videos. I had a guy that lived on a train and had kids come to his train.
Oh, gosh.
To do German.
All right, so let's talk about what happens, and stop talking about Spanish. Let's talk about what happens when we have a small sample. All right, so when you have a small sample size, as long as the underlying distribution is normal, we can use a t distribution to help us get the confidence intervals. So the reason why, of course, is that, remember your t distribution, what goes on top of the t distribution? The normal distribution, and what goes on bottom? A chi-squared, square root of a chi-squared divided by its number of degrees of freedom, right? Remember that? All right. All right, so let's see how we can work with this to help us understand why this works for small samples, especially it's small samples if we don't know the variance of the population. If we know the variance, if we actually know the variance and it's normal, you do it the same way we did the previous ones. You still use z's. Okay, so use z-scores if you know the variance. But again, if you're doing this stuff, why would you be doing sampling if you already know the population parameter, right? The chances that you actually know the population's variance is pretty small. Okay. All right, so let's see why this works. So how will we do this in general? So if we want to get a standard normal based on the sample, you would do the x bar minus mu over sigma over the square root of n, right? That's how you get standard normal for the x bar, right? With regard to the sample, what has the chi-squared distribution with regard to the sample? What thing do we know has a chi-squared distribution with regard to the sample? Or at least a multiple of it is a chi-squared distribution. The sample variance, right? So I would take the square root of n minus 1 s squared over sigma squared, that whole thing, and divide it by n minus 1. This is a t distribution. That looks ridiculously ugly, doesn't it?
I think it looks pretty.
You think it looks pretty? No, of course you do. Okay. But this simplifies. Okay? Notice that the n minus 1s here cancel. Right? If I took the square root of the sigma squared, I will get sigma. It's on bottom in the bottom. So when we flipped it, it would be on top. It's going to cancel with that one. Right? If you go through all of this, what this simplifies to is you get x bar minus mu over s over the square root of n. If we go through and simplify all of that, that's what we get, isn't it? Which has the same form as it did before, except that we have an s instead of a sigma. Right? So when we construct the confidence intervals, they get constructed in the same way, except that we have to use the t distribution bounds rather than the normal distribution bounds. Because now we have a t distribution. How many degrees of freedom are there in this t distribution, by the way?
8.
Okay, for this specific example, it's 8. In general, it will be n minus 1, right? Because that's what's in the denominator here.
Yeah.
Okay. Right? That's how many degrees of freedom there are. So, in this particular one, in this table I actually do have, I did make a picture of it. Where did I put it? There it is. All right. So this is in your book on page 586. This is your t distribution. We just said there are, Grace just told me there's 8 degrees of freedom, right, for this one? Okay. So instead of looking for a z sub alpha over 2, we're going to look for a t sub alpha over 2 in the table. What was the confidence interval we're doing? So what's alpha? 0.05, so alpha over 2 is 0.025, right? So we're looking at this column. Ooh.
No, I wasn't.
We're looking at this column, the 0.025.
Yeah.
All right. And we're going to go to 8 degrees of freedom, which is that line?
Yeah, that one.
That one? The 2.306?
Yes.
This one here?
Yeah.
Okay. The 2.306. So that's your t that we're going to use instead of the z. That's it. It's exactly the same, except you go to the t table rather than the normal distribution table. But it's exactly the same process. You just get your value that you're using for that that helps you get to the margin of error, you get that value from the t-table. So again, this is small sample, so less than 30, small sample. Population variance unknown. Both of those have to be true. If your population variance is known, and you know it's normal, you go to the normal distribution regardless, small or big. Okay, you go to this if underlying distribution is normal, small sample, population variance unknown. You go to the t-table. Yeah.
With this question, did they tell us to use the t-distribution, or like is there like a cutoff for what size?
30 is the cutoff.
Okay.
Actually, there's the cutoff because I can't go any higher if you're using the table. With Excel, you can still use whatever you want, but with the table, you get cut off at 30. Notice that as you go off to infinity, of course, you get the z values. So notice we had that 1.96 earlier. That's the same z. Michael?
Dr. Lee was talking about being able to use, like, well, she said she wanted, did she say she wanted us to use the t-value more? Like, the t-value was more accurate?
No.
Oh, well,
T was more.
okay.
They said T was better than nothing.
Okay.
Yeah.
So, like,
Ah.
All right, so let me show you how to do this in Excel in the last 2 minutes that I have. Since it just dinged. All right. What's that? It's still mu. It's still the mu that we're looking for, yeah. All right. It's still we're still doing the confidence interval for the mean. It's just small sample. With
That one, your interval would be like -2.3 or whatever that number.
well, let's just type it in real fast here. So we had the 21.5, 18.95. Oops. Whoops. Wow. 0.4. I'm too fast. Can you type? Oh my goodness. I'm too fast for the Bluetooth, apparently.
Too good.
Well, I used to run a cash register back when I worked at Sears, so it'd be one. Yeah, before they had, scanners. All right. So, if I want to do the mean, average of those, and the standard deviation of those. All right. So, notice the t distribution is built in here too. You can use any of these. We want to use a t dot inverse. The probability was a 95% confidence interval, so I want 0.975, and the degrees of freedom here was 8. So you get that 2.306 value that we saw on the table. So again, it's just like what we did for the normal inverse. Okay. So then you still would find your values by doing, if you do, the mean was here, right? The 20.9, right? And then you subtract off the t value times the standard deviation divided by the square root of the sample size, which was 9 in this case. It's the same format. You're just using the t as opposed to the z. Yeah. It's the exact same format. All right? We'll do a couple more examples of this next time and then talk about difference of means as well. And it's going to be the same concept. It just changes how we calculate the standard deviation. Have a good one.
Remind me of the 0.975.